I'm Anna Stuhlmacher, and I will be presenting Professor Johanna Matthews and my paper. This paper looks at using the water network as a flexible load to provide local services to the power distribution network. So I'll first briefly talk about the motivation of this work. There's growing interest in optimization and control of coupled critical infrastructure systems, such as water, power, gas, and district heating networks. The potential benefits of co-optimizing multiple critical infrastructure systems include improving reliability and flexibility, as well as decreasing capital and operational costs. In our work, we consider the water distribution network and the power distribution network. These networks are interdependent since water pumps are loads in the power distribution network, and elevated water storage tanks in the water distribution network can shift pumping in time. Both networks are facing new operational challenges, such as increasing consumer demand in the water distribution network and more uncertain distributed energy resources in the power distribution network. Given this, our goal was to utilize the water network's flexibility to support the power distribution network, in particular provide voltage support. So there's two challenges when formulating this problem. The first is that both water and power distribution networks include nonlinear and non-convex constraints. And this is addressed by using convex approximation and relaxation techniques. And the second is that both networks are subject to uncertainty, such as power demand uncertainty. And we address the power demand uncertainty by forming a real-time control policy to respond to the demand forecast errors. Since the water network and power network are both critical infrastructures, we care most about feasibility. So we formulate the problem as a chance-constrained optimization problem, which considers both the network constraints and the uncontrollable power demand uncertainty. We jointly solve for the optimal water network pumping schedule and an affine real-time control policy to respond to the power demand forecast error. So I will first review the formulation for the water and power distribution network. The water distribution network is characterized by the hydraulic head at each node and the volumetric flow rate of water through each pipe. And in order for the water network operation to be realistic and safe, the hydraulic head at each node, the pump flow rates, and the tank levels all have upper and lower limits. And lastly, there are three constraints that are nonlinear or non-convex quality constraints. And using the method from reference 2, we approximate the quadratic pump performance curve, as additionally we replace the quadratic pump power consumption and pipe head loss equations with their convex holes. For the power distribution network, we consider a radial network. The loads in the power distribution network are composed of the uncontrollable net load and the controllable water supply pump load. We limit the voltages at each bus and phase. And in order for the power distribution network to be convex, we use a linearized three-phase unbalanced power flow model. And the formulation neglects the loss terms and assumes that the voltage imbalance is small. So next we include the power demand uncertainty and then formulate the control policy. We denote the power demand forecast error at bus K, phase V, and time T as this tilde rho value, and the auxiliary random variables, which are dependent on the power demand uncertainty, are denoted with a tilde. The purpose of the control policy is to adjust the pump operation to compensate for power demand forecast error when there is a voltage constraint violation. And because of this, it can be thought of as a corrective control policy. However, not all power demand forecast errors require corrective actions by water pumps. And to incorporate this into the formulation, we introduce an auxiliary binary variable tilde s that equals 1 when there's a minimum or maximum voltage limit violation, given the scheduled pump power consumption and the power demand uncertainty realization. And when tilde s equals 0, no corrective action is needed and the pumps maintain their schedule. So the control policy is shown at the bottom, where the control policy parameter C sub E is a row vector, and it is multiplied by the power demand forecast errors for all buses and phases that have loads. This determines the corresponding change in flow rate for a pump, denoted tilde X sub E. And despite the pump flow rate adjustments shown here, the pumps and tanks must provide the same amount of water to the network. Here I outline the mixed integer convex chance constraint problem. We want to minimize the cost of the scheduled water network pumping operation and the flexibility cost associated with adjusting the pumps from their schedule in real time. So in order to penalize excessive control actions, we set the flexibility cost as the Frobenius norm squared of the control policy parameters. And then we solve the chance constraint problem to determine the scheduled pump and tank operation, as well as the control policy parameters. And this problem is subject to both networks constraints, as well as a chance constraint, where the constraints should be satisfied jointly for a probability level of at least 1 minus epsilon, where epsilon is the violation level. The constraints included in the chance constraint are the control policy and the stochastic equivalent of the network constraints given the power demand uncertainty. To solve this problem, we use the scenario approach for convex programs. And in the scenario approach, the problem is solved robustly for a certain set of scenarios. And the number of scenarios that you need to include for a convex problem is determined by the user selected violation level epsilon and the confidence level psi, and is determined by this function n. To use the scenario approach for convex problems, we need to simplify the formulation. We do this by removing the binary variable and applying the control policy to all scenarios. The problem then becomes a convex quadratically constrained program. While there exists scenario approaches tailored to the mixed integer random convex programs, these methods require significantly more scenarios than the approaches for convex problems, in addition to requiring a more computationally intensive mixed integer solver. To illustrate this, I compared the solutions found by solving the mixed integer convex problem and the simplified convex problem with a fixed number of scenarios for a coupled water distribution network and power distribution network, which is described after this. We observed in this test case that the solutions are essentially the same, but the convex problem takes significantly less time. If the solutions were different, the main concern would be if we inadvertently caused constraint violations by always applying the control policy, regardless of whether the system needed it. Next, I'll present the case studies we did. We used a coupled IEEE 13 bus test network and a water distribution network from the literature, where the pumps are balanced three-phase loads in the power distribution network. We looked at several single period and multi-period cases that are designed so the power distribution network is near the minimum or maximum voltage limit constraints. And the power demand forecast error was generated using a truncated Gaussian probability distribution. The error at bus K, phase phi, and time t had a mean of 0 and a standard deviation of 4% of the net power demand at that bus and phase. And to evaluate the reliability of our solutions, we use the Monte Carlo method to test whether all water distribution network and power distribution network constraints are satisfied for 100,000 randomly generated uncertainty realizations. The empirical violation probability is calculated as the percentage of realizations for which at least one constraint is not satisfied. So I'll first show some illustrative results from this approach. This figure shows the scheduled pump and tank operation for two different cases. In the left column, case A has constant high water and power demand. And then in the right column, case B's water and power demand starts high and then decreases in the next two time periods. The blue line shows the schedule for the chance constraint approach, and the red dashed line shows the optimal schedule based only on the forecasted demands. We can see that the chance constraints pump and tank operation vary more between periods than the deterministic schedule. This is because the scenario approach's schedule needs to ensure that the forecast error realizations do not cause power distribution network constraint violations. So for example, pump 1 is less expensive than pump 2, but it is located at a bus that is closer to its minimum voltage limit. In order to satisfy each scenario's voltage constraints, pump 1 must decrease and pump 2 must increase, which is a more expensive operating point. And in case B, the tank's net outflow is increased to meet the reduction in pump 1's flow rate. And later, when demands are lower, extra pumping is used to refill the tank. So I've overlaid light and dark blue bands, and the edges of the light and dark blue bands show the largest and average pump and tank adjustments from the scenario approaches scheduled made by the control policy in the presence of a voltage violation. In these cases, the bus voltages are near the minimum voltage limit, and the control policy is working to raise the voltage levels by decreasing pump power consumption. So for case B, the bands are much smaller since the system is operating further from the power distribution network constraint violations, and less real-time control actions are needed. Specifically, pumping is shifted to periods 2 and 3 when there is less power demand.
Anna, you have 1 minute.
Okay. And this is an example of using the real-time control policy when there is a voltage limit violation. The plot shows the three-phase linearized unbalanced voltage profiles associated with a power demand scenario before and after the control policy adjusts the pump operation. As we can see, the initial voltage profile, which are the green lines, are outside the voltage limits, and then once the pumps are adjusted, the voltage profile is within the voltage limits. In this case study, the voltages on phase C are most likely to cause lower voltage limit violations, and consequently, the magnitude of the control policy parameters associated with the buses and phases within this inset here are the largest. And we see this small shift in voltage profile because the chance constrained optimization problem has no incentive to correct the voltage any more than necessary, since the approach focuses on feasibility and the objective function seeks to minimize the real-time pump adjustments. And lastly, we look at the performance of the schedule and control policy. So for different standard deviations and user-selected violation levels of case A and B, I have shown the total cost and the empirical violation probability. As expected, when the user-selected violation level epsilon is reduced, the total cost increases. And this is because the schedule and control policy must become more conservative to handle more scenarios. And we see that the empirical violation probability is much lower than the user-selected violation level, which is typical for the scenario-based approach. Additionally, the user-selected performance guarantees only hold for the convexified problem and not the original non-convex constraints. So in this work, we were able to successfully utilize the temporal and spatial coupling of the water distribution network and power distribution network to provide voltage support in the power distribution network. And the approach is computationally intensive, and given the nature of the scenario approach, produces a solution that has a high cost and a high reliability. And listed below is some future work. All right, questions?
Okay, thank you very much, Anna, for the nice talk. I have a question from Dan Molchan. So he says he would suspect that the dynamics of the water network operate at time scales that are quite a bit slower than the dynamics of the power system. And if he understands your formulation appropriately, you don't consider the water system dynamics. Does this have an impact on the feasibility of your solution in real-time operation, or it's not an issue?
In this problem, we're looking at like 1 hour time steps, which is usually the kind of planning and operation time steps that are used in the water distribution network. But I guess if using smaller, the pumping can be changed on smaller time steps, and we're not necessarily looking at that. We're just assuming a constant water demand for the entire time period, if that answers the question.
Okay, so he's following up and he's asking if you could describe the mathematical formulation for the water system convexifications.
Oh, yes, okay. So there are 3 constraints in the water network that make it so it's not convex constraints. They're 3 quadratic equality constraints. So the first one, we look at approximating it by taking the quadratic term is a very small negative number. So we ignore that term, and then the second 2 quadratic constraints take the convex hull. And so then it becomes a convex quadratically constrained formulation.
Okay. So another one, are the total costs identical for MICP and CP models in any case study? Or is there no gap between models with and without binary variables?
Right, so in the test case that we looked at, they were very similar, but I don't think it could be said for any test case. And the main concern would be if by neglecting the binary variable, you cause a voltage violation by applying a control policy when you don't need to apply a control policy.
Mm-hmm. So Jonathan Dumas asks whether it's possible to address this problem by using a robust approach with budget of uncertainty.
Yes, I think it would be, and I think in the problem that we have it's very computationally intensive, and this might be a way to speed it up.
Mm-hmm. Okay, I have a question. So you solve a problem that is originally non-convex, and after right. the relaxation, you are applying the scenario approach that can provide only guarantees for the relaxation, right? So
right.
Your outcome in the end, so the solution you give, what is the strength of the solution with regards to the original problem? Is it a posteriori you're checking what is going on because you saw some results for the original, I guess, but it's not that you can a priori say that the theoretical probabilistic guarantees can be satisfied, right?
Correct, yeah. We can't give performance guarantees on the original non-convex problem in this case. And in this paper and in a follow-up one, we look at testing how the performance of this method is on the original non-convex solution. And I think the largest thing that we see is that There are more voltage violation happening, but they are very small. And so this chance constraint approach doesn't look at like the magnitude of the violation, since most of them would be so small as to be like ignored. But yes, that's correct that it doesn't have performance guarantees.
Okay, okay. I think that's it. We are on time to go to the next one. Thank you very much, Anna.